Good afternoon, everybody. Today I am going to tell you about the reduced equation of state, and from it emerges the law of corresponding states and the significance of the law of corresponding states. So first of all, let me tell you about the reduced equation of state, and before going to that, I would like to tell you a bit about the critical phenomena. I have taught you about the critical phenomena. So critical phenomena is the smooth merging of the gas and the liquid state, and when this and in this state there is no perfect boundary between the liquid or the gas, means that the boundary between the liquid and the gas just disappears and the density of the whole becomes equal. This state is known as the critical state, and this phenomena is known as the critical phenomena. During this state, when a gas is in its critical state, the temperature is known as the critical temperature, the pressure is known as the critical pressure, and the volume is known as the critical volume. So from the study of the critical phenomena, it has been seen that the deviations from the ideal behavior, they depend upon the state of the gas relative to the critical state. So this led van der Waals in 1881 to express the pressure, volume and temperature of the gas as fractions of critical constants Pc, Vc and Tc, and call them as the reduced variables. And this gave us the reduced equation of state, and from it came the important generalization of law of corresponding states. So let me begin with the derivation of the reduced equation of state. We have here these reduced variables, as I just now told you, which were derived by the van der Waals. Pi is equal to P upon Pc, phi is equal to V upon Vc, and theta is equal to T upon Tc. This pi is known as the reduced pressure, phi as the reduced volume, and theta is the reduced temperature. And from this, we get that P is equal to pi Pc, P is equal to pi Pc, V is equal to phi Vc, and T is equal to theta Tc. So this state of the gas, the pressure, volume and temperature are expressed as the reduced variables and the critical constants Pc, Vc and Tc. So here the reduced variables are pi, phi and theta. So let us begin with the van der Waals equation. We all know that the van der Waals equation for 1 mole of gas is given by P plus A upon V square, V minus V is equal to R. So this is the van der Waals equation. Now let us substitute the values of P, V and T from this equation. So what we get, P is equal to pi Pc. So we substitute P for pi Pc, V for phi Vc, and since it is a square, we keep it as phi Vc whole square. V is again phi Vc minus V is equal to R, T is not theta Tc. So it will be R theta Tc. Let it be equation number 2. So now, as we all know that the critical constants of gas, the Pc, Vc and Tc, in terms of van der Waals constant are expressed as P is equal to A upon 27 B square, Pc is equal to and Vc is equal to 3B. And what is the value of Pc? Pc is equal to 8A upon 27. By now you are quite familiar with these constants, that Pc is equal to A upon 27B square, Vc is equal to 3B and Tc is equal to 8A upon 27R. So the critical constants in terms of van der Waals constant, these are the values. Pc is equal to A upon 27B square, Vc is equal to 3B and Tc is equal to 8A upon 27R. So now we will substitute these values in this equation number 2. So Pc is equal to A upon 27B square plus A upon 5, Vc is 3B square, 5 Vc is 3B and minus B comes over here, R theta and Tc is 8A upon 27 RB, we have substituted it. And what we got is equation number a step, next step. We have simply, this 3 is a square, I have made it 9, b square, 5 square, and this is the same equation has been repeated. Now, when we have to arrive at some conclusion, we usually assume or multiply both sides of the equation with some factor, and here we have multiplied this equation number 4 by 27b square upon a. We have multiplied it by 27b square upon a. Or in another way, we can say that we have divided it by a upon 27b square. It's the same thing. Just to reduce a step, I am saying that we have multiplied it by 27b square upon a. What we get, 27b square upon a gets cancelled, and we get 5. Multiply this thing also. What we get is 3 upon 5 square. Why? Because a gets cancelled with a. A gets cancelled with a. And here it is 27b square. 27b square. B square will also get cancelled. And from 9 we will get 3. With 9, 3s are 27. So we will get 3. And here this is another factor. This is one factor and this is another factor. And obviously we will multiply one factor only. Suppose there was plus sign, then we would have multiplied it also with 27b square. Since this is a factor, so we multiply only one factor. So this comes out to be 3, 5 minus 1, and we have taken out b to be common. B is common over here and we have taken it out. And here when we multiply this also with 27b square upon a, what we get? 27 will get cancelled with 27 and b will get cancelled, but one b will be remain over here, and this a will also get cancelled, and this r will get cancelled by this r. So what's remaining here? 8 theta and 1 b, which was from 27b square. 1 b has been cancelled and 1 b remains over here. So finally what we get is 5 plus 3 upon 5 square into 3 5 minus 1 b is equal to 8 theta b. This is our equation number 5. Now as you can see that we are having b this side of the equation, in the left hand side as well as in the right hand side, we are having this b. This b also gets cancelled. So finally we get equation number 6, which is 5 plus 3 upon 5 square into 3 5 minus 1 is equal to 8 theta. This equation number 6 is known as the reduced equation of state, and what we see in it is that it is devoid of, it does not have a and b, which are the van der Waals constants. So when we are not having the van der Waals constant, this means that this is a general application, this is a general equation, and it can be easily applied to all the liquids and the gases, because a and b are characteristics of the gas. And when they are not present, and moreover R is also not present in it, so all the constants are not present in it. So this is a general equation and it can be applied to all the liquids and the gases. So this is our reduced equation of state. So this means that if two gases, two substances are at the same reduced volume and same reduced temperature, then they are at the same reduced temperature also. This is known as the law of corresponding states. Suppose we are having a gas A and there is another gas B, and they are at the same reduced temperature and they are having the same reduced pressure, then definitely they will have the same reduced volume. So this is a very important generalization of reduced equation of state, that if two gases are at the same reduced temperature and pressure, then they will be at the same reduced volume. This is the law of corresponding states. Now I will tell you about the significance of this law of corresponding states. We have arrived at this equation which is the reduced equation of state, 5 plus 3 upon 5 square into 3 5 minus 1 is going to 8 theta. So a little bit rearrangement over there, and what we get, 5 plus 3 upon 5 square will be equal to how much? 8 theta divided by 3 5 minus 1. Since these two are factors, when we bring it over here, it will go in the denominator. So this comes out to be 3 5 minus 1. So let it be equation number 7. Again, a bit more of rearrangement. 5 will be equal to how much? 8 theta divided by 3 5 minus 1. And when we bring this to this side, this is plus 3 upon 5 square. When we will bring it to the other side of the equation, definitely the sign will change. From positive, it will become negative. Minus 3 upon 5 square. This is equation number 8. Now, when we are telling you about the significance of this law of corresponding states, we see that pi is equal to 8 theta upon 3 5 minus 1 minus 3 upon 5 square. Now, if the reduced volume, which is pi, this is kept constant. If phi, the reduced volume, it is kept constant. This is reduced volume. And if we keep it as constant, if this phi is constant, then we will get a linear relationship between the reduced temperature and the reduced pressure and the reduced temperature. When phi is kept constant, then we will get a linear relationship between reduced pressure and the reduced temperature. Just like we can say in an ideal gas, we also have the linear relationship between pressure and temperature when the volume is kept constant. So this is related in a very similar way like we have for ideal gases, in which the pressure and the volume is related to temperature. So another significant point for this law of corresponding states is that when the compressibility factor means Z, PV upon RT, is plotted against reduced pressure pi for different gases studied at various reduced temperatures, then the values for the different gases lie on more or less the same curve. So this shows that all the gases in the corresponding states deviate almost equally from the ideal behavior. So these are the two most significant points for this law of corresponding states, and you have to go through them because there are numerous numericals which are being framed on this equation. And okay, that was all about the reduced equation of state and the significance of the law of corresponding states. Thank you.